Good afternoon, lads and ladies. Welcome back to our final meeting of Calc 2. It's crazy to think that this semester has gone by. It seems like just the other day we had our very first class. So today we're going to conclude the content for the course. The last little bits of things we need to talk about are arc length in the parametric setting, kind of wrapping up a little bit from last time. And then polar coordinates. Polar coordinates are pretty cool. They're conceptually, I think, a little bit challenging. The geometry can be somewhat hard, but if you've been kind of lost in the sea of analysis type things with series, I think you'll enjoy this a little bit more. This is much more kind of spatial reasoning, thinking about geometry than it is working with symbols. So here we go. I've found that the purple shows up best against the graph paper, and I'm out of printer paper today, so I'm going to be using this graph paper. A purple pen. This is MAC2312, section 004. It's a lecture. And today is the 22nd of April, 2021. Today, we're going to finish parametric curves. And we're also going to talk about polar coordinates. I'm supposed to assume that you guys all remember polar coordinates from trigonometry, but I think that's probably not the case. So I'll be going through a little introduction here before we go whole hog into doing calculus and polar coordinates. But before we go there, we need to talk a little bit more about parametric curves. So the last sort of thing that I wanted to show you guys here was arc length and surface area. And the derivations of each of these are kind of fun. So even though it's a bit time consuming, I'm going to show you where they come from. So let's get to it. Arc length is what it sounds like. If I give you a curve, I want you to imagine that that curve is a piece of string. If I kind of stretch it out, not stretch it out, but kind of pull it out flat, how long is that? So the question here is, can we find the length of a curve? So again, usually with parametric curves, we're imagining these as like paths that particles travel along. I like to think of it as a little ant kind of walking around on the page. So the arc length question is like, how far did the ant walk in going from the initial point to the terminal point? I'll tell you the result and then I'll prove it. You can use this, remember, any curve, whether if it's given to you parametrically, you can use this theorem right away. If you're given a curve that's not in parametric form, if you're given like y equals f of x, you would parametrize it and then use this form. So you can use this theorem to find the length of any curve, even the ones that we were studying earlier in the semester. But I'm going to phrase it as though it's given as a parametric curve. So to find the length of the parametric curve x equals, I'll just call it x of t, and y equals y of t from the point associated with t equals a to the point associated with t equals b, we compute the integral from a to b of the square root of, whoa, sorry guys, I think my document camera just decided to turn off. All right. You back yet? No, hurry up. I don't know why I did that. The power cable's plugged in and stayed. And it just crashed. Looks like it's coming back to life here. So yeah, to find the length of the parametric curve, whose x equation is, I'll just call it x of t, and y equation, I'll just call it y of t, from t equals a to t equals b, you compute the integral from a to b of the square root of dy dt squared plus dx dt squared dt. And kind of classically, traditionally, we would call this little s. Little s is the classical symbol for arc length. Proof. Of course, here we need x of t and y of t to both be differentiable functions of t because this involves their derivatives. So you can assume that the parametric curve is smooth. If both your x and y functions are smooth, then your curve is smooth. Here's my x-axis, here's my y-axis, and I'm going to take a curve, we'll just say something like this. My initial point is over here. This is the point associated with t equals a. So this would be like x of a, comma, y of a. And my terminal point over here is the point associated with t equals b. So that would be x of b, comma, y of b. Kind of the idea here, this integrand should remind you of something. It kind of looks Pythagorean, right? Like a squared plus b squared equals c squared. If you solve that for c, you get the square root of a squared plus b squared. There's a good reason for that. We partition the time interval, the t interval, a, b, into equal length subintervals. So I'll call that, like, imagine I don't have a t-axis in the picture here. So imagine down here I have the time interval from A to B. This is kind of like your slider in Desmos, right? Where you can move the slider around and you see the point move on the curve. I'm going to chop this up. I'll call A T0. I'll call B Tn. And then, you know, we'd have like T1, T2, T3, all the way out until we get to Tn minus 1 and then Tn. So this is my time interval. Each one of these times, T1, T2, T3, is associated with a point on the curve. So like maybe here's the point associated with T1. Maybe here's the point associated with T2. Maybe here's the point associated with T3. And they're not going to be equally spaced along the curve, right? Because that particle could be moving really fast here and really slow here. It all depends on the functions x and y. But what we end up with is, from that partitioning, we get a bunch of points on the curve. Now, just to make life simple, I'm going to call the initial point P0. I'll call this next point P1. The next point here I'll call P2, and so on. So P0 is the point associated with the time T0, or A. P1 is the point associated with the time T1. P2 is the point associated with the time T2, and so on. So it'd be like P3. I'm going to put some dots in here. We'll call this P4. These two I'm going to call Pi minus 1 and Pi, just like generic points. They're two consecutive generic points. This would be Pn minus 1, and this would be Pn. So by partitioning the time interval, we get a bunch of points along the graph of my parametric curve. And now between those two generic points, pi minus 1 and pi, I'm going to approximate the arc length using straight line segments. In fact, that's what we're going to do everywhere. So for the arc length between pi minus 1 and pi, I'm going to just consider the straight line segment. And the idea is here, I'm going to send n to infinity. So I'm going to get all of these points closer and closer and closer together. So we'll end up with a really good approximation. Now on this particular one, I'm going to draw a right triangle. Let me go ahead and fill in the straight line segments for each of these. It's not exact, right? This is definitely just an approximation. Between these two, I won't connect because I don't know. There could be a bunch of little points in between here. And similarly, between these two, I'm not going to connect because there could be some points in there. That's those dot, dot, dots. But this is the idea. So, you can kind of see that the purple length through here is pretty close to those little blue lengths. The purple length is curvy, so it's hard to calculate. But the blue lengths are straight lines, so they're easy to calculate. I'll call this delta xi. It's the change in x in the ith subinterval. And this distance I'll call delta yi. It's the change in y over the ith subinterval. Then my arc length S is approximately the sum from I equals 1 to n of the distance from pi minus 1 to pi, right? It's the distance from p0 to p1, from p1 to p2, from p2 to p3, from p3 to p4. All of those little distances added up. And at my generic points here, we can see that the distance from pi minus 1 to pi, take this over here, the distance from pi minus 1 to pi squared is equal to delta xi squared plus delta yi squared. That is just the Pythagorean formula. Right? A squared plus b squared equals c squared. This is a little right triangle. So this squared plus this squared equals this squared. Which means that the object in my sum here, which is the distance from pi minus 1 to pi, is the square root of these things. So I'm going to plug that into my formula here. This is like a Riemann sum, but it's a Riemann sum for lengths rather than for areas. So because the distance from pi minus 1 to pi is this square root, the sum of those distances is the sum of those square roots. Excellent. Everybody with me so far? Take a second, make sure you're comfy. Turn this off, get my feet out of the way. My goal is to make this look more and more and more like a traditional Riemann sum. So I'd like to have, remember my integral here is a dt integral. Kind of, you can compare the pieces, right? Compare this sum to the integral that we're trying to prove is equal to the arc length. I want a dt at the end. I don't have any t stuff in here, right? Just x and y stuff. So in order to kind of get closer to this, I'm going to introduce a delta t here. We know as n goes to infinity, delta x becomes like dx, delta t becomes like dt. So the next step is a slightly clever algebra move. I'm going to multiply by dt over dt. And I get sigma I from 1 to n square root of delta xi squared plus delta yi squared times delta t over delta t. And now the delta t downstairs, I'm going to move inside the square root as the square root of delta t squared. So this is the same as sigma I from 1 to n square root of delta xi squared plus delta yi squared times 1 over delta t squared. And then the delta t that was upstairs stays outside the square root as delta t. So this delta t downstairs came inside the square root as delta t squared. Everything else stayed the same. Now I distribute that delta t, and I get sigma I from 1 to n square root of delta xi over delta t all squared, right? Delta xi squared over delta t squared plus delta yi over delta t all squared times delta t. And this is exactly the Riemann sum for the integral at the start. So we're done. We've actually proved this. Now, as n goes to infinity, we see that s is exactly equal to, no longer shaky equal sign, but is exactly equal to the limit as n goes to infinity, sigma I from 1 to n square root of delta xi squared, delta xi over delta t all squared plus delta yi over delta t all squared times delta t. And this is the Riemann sum for that integral. This is the integral from a to b of the square root dx dt squared plus dy dt squared dt. So that's the proof. And see, that is the formula we were trying to prove. The order under here, these are being added. So dy dt squared plus dx dt squared, or dx dt squared plus dy dt squared, that doesn't matter. So that concludes the proof. So I'd like to show you an example or two. These arc length integrals, they can be quite tricky. This integrand, with the square root of stuff squared underneath, kind of looks trig subby, and often they are. These problems tend to have tricky solutions, sometimes requiring trig sub. But yeah, this is the formula we need to remember for arc length. So let me grab an example. If I just make up a random example, odds are it won't have a nice solution because, again, these integrals can be quite gnarly. So I'm going to grab one from the book. Nice example here. It's in chapter 10, parametric curves. Arc length. Here we go. You see here their derivation, same picture. And they go through it in the same sort of way. They're calling the arc length L. They're using alpha and beta instead, but it's the same thing. So this is what we need. Sure, why not? We'll do the unit circle. I can find the arc length of the curve x of t equals cos t, y of t equals sine t, where 0 is less than or equal to t is less than or equal to 2 pi. So we know from last time that this is the parameterization of the unit circle. What we're going to be finding here is the circumference, the length or circumference of the unit circle. And we know what that is. What is the circumference of the unit circle?
Two pi.
Yeah, very good, right? The circumference of a circle is pi times its diameter, or 2 pi times its radius. The radius of the unit circle is 1, so we expect 2 pi here. Let's do it. This would be the integral from 0 to 2 pi of the square root of dx dt squared plus dy dt squared dt. So what is dx dt? Well, it's the derivative of cos t, which is negative sine t. And dy dt is the derivative of sine t, which is positive cos t. So my arc length integral becomes the integral from 0 to 2 pi of the square root of dx dt squared, that's negative sine t squared, plus dy dt squared, that's cos of t squared. And the integral here is done dt. Now the square of negative sine t is sine squared t, right? The negative goes away, so we get integral square root sine squared t plus the square of cos t is cos squared t. And what is sine squared t plus cos squared t? Can we simplify that at all?
Equals 1.
Yeah, it's 1. Very good, right? By the first Pythagorean identity, that is equal to 1. And the square root of 1 is just 1. So this is the integral from 0 to 2 pi of 1 dt, or just dt. Antiderivative of 1 dt is just t. So this is t evaluated from 0 to 2 pi, which is 2 pi minus 0, or just 2 pi. Thank goodness. We were pretty sure that the unit circle had circumference 2 pi, and indeed it does. Now things get more challenging here as your curve gets more complicated. So I'd like to look at least one more example. The book has a neat thing here. They show if you use a different parametrization, if you use sine of 2t comma cos of 2t, this would have you walking around the unit circle twice as t goes from 0 to 2 pi. So the arc length there would be 4 pi. So it's important that when you parameterize your curve, you're aware of what it is you're looking at. This parametrization has us walking around the unit circle exactly once counterclockwise. If we ran out to 4 pi here, then we would walk around the circle twice. Or if we left this as 2 pi, but had sine of 2t and cos of 2t, we would be walking around the circle twice as fast, and we would go around it twice as well. So again, really understanding what these parametric equations and parametric curve give you are crucial to interpreting the arc length integral. Most of the time that won't be an issue, but it is still nice to know. Before we get to surface area, I want to do something well, we're not talking about the cycloid, but something else. So find the exact length of the curve. I know they're in here. There we go. What looks like fun? Oh yeah, 43 is interesting here. I think this comes out to be something quite tricky. But before we look at it, let me talk a little bit about this curve. That's the one we're going to do. I want to find the exact length of the curve. X of t equals t sine t. Y of t equals t cos t. And they say from 0 to 1. Sine t. Right. Any idea what this curve looks like? If it was just cos t and sine t, that was the unit circle. Let's look at some variations on that. Okay. So cos t comma sine t, 0 to 2 pi. This is our normal unit circle, right? This is the guy we did in our previous example. What do you think happens if I switch the sine and the cosine? Nothing happens. Sine t comma cos t also gives you the unit circle, but it traces it in the opposite direction. So if you switch sine t and cos t, a few things happen. Your terminal point is, your starting and terminal points change. Your initial point is going to be at the north pole, because when you plug in 0 for s or for t, you would get 0, 1 instead of 1, 0. But this still satisfies the same Pythagorean thing that x squared plus y squared is equal to 1. So you're still going to be on the unit circle. You're just going to be walking around it in the other direction, starting at the north pole rather than starting at 1, 0, rather than starting at the easternmost point. So that's still not our guy. Our guy is t sine t, comma t cos t. So not only have we switched sine and cosine, we've also multiplied by a t in both. We saw last time, bring this guy back. Oh, no, sorry, leave him out. We saw last time that if I multiply by 2 in both of these coordinates, that I'm going to have a circle of radius 2 instead. If I multiply by any number in both coordinates, I'll change from the unit circle to the circle of radius that number. But what if I multiply by t? I'm sorry, it's an s down here, it's a t here. Well, then I have a circle whose radius grows as we go around. That's a spiral. Yeah, there we go. So I'll start this at 0. So rather than having a circle, if your radius, so r sine t comma r cos t would be a circle of radius r. If you let that radius be a variable like t that grows as t grows, you're going to end up with a spiral. There's actually a lot of different ways to do this. The spiral you get here is what's called a Archimedean spiral. Let me send this out to something like 16 pi, and here, what's this? 16 pi. An Archimedean spiral is one whose radius grows at a constant rate. So kind of the gaps between any two concentric layers in the spiral is a constant. There are also things like logarithmic spirals, exponential spirals. That golden ratio spiral that you may have seen shows up if you use e to the t here instead of just t as the radius. It's pretty cool stuff. So what we're trying to do in this problem is find just a little snip of this. We're trying to find the length of this thing as t goes from 0 to 1, which is just this tiny, tiny little bit. This is what we're looking for in this problem. It's just this little length. So how do we do it? Well, we follow the same rules. My arc length is the integral from a to b of dx dt squared plus dy dt squared, all under the square root, done with respect to t. Here, dx dt and dy dt both require the product rule to calculate. So if I want to differentiate this with respect to t, I use my product rule. First, I'll differentiate the t, leave the sine t alone. That'll give me 1 times sine t. And then I add to that what I get when I differentiate, when I leave the t alone and I differentiate the sine t. So that's going to be t times cos t. Similarly, dy dt is done with the product rule. I'll have 1 times cos t, and then t times the derivative of cos t. The derivative of cos t is negative sine t, so this is going to be minus t times sine t. And I plug that stuff in. I come down a little further so I have room. My a and b, the t values where I'm starting and stopping, are 0 and 1, so it's integral 0 to 1, square root of dx dt squared. That's this whole thing squared, and we need to put it in parens and FOIL it out. So that's sine t plus t cos t squared plus dy dt squared, which is cos t minus t sine t all squared. And all of that is under the square root. And I have my dt at the end. We can FOIL this apparatus out. So underneath my square root, I'll have sine squared t plus 2t sine t cos t plus t squared cos squared t. That's the first piece. And then we'll have plus cos squared t minus 2t cos t sine t, or minus 2t sine t cos t, and then plus t squared sine squared t. Holy shit, it just barely fits. I'm not gonna have room for the dt, sorry. But of course, there is a dt at the end here. A little bit messy. But if we start matching pieces up, I have a sine squared t here and a cos squared t here, and we'll be able to combine those to 1. I have a plus 2t sine t cos t and a minus 2t sine t cos t. Those will cancel out perfectly. And then I have a t squared cos squared t plus t squared sine squared t. So putting all the bits together, we get integral 0 to 1 sine squared t plus cos squared t. I'll write it for now. Sine squared t plus cos squared t. The 2t sine t cos t's cancel perfectly. And then I have t squared cos squared t plus t squared sine squared t. And all of this is under the radical, still a dt at the end. These two guys add up to 1. And these two guys, I can factor out a t squared, and then what's left is cos squared t plus sine squared t, which again is 1. So this piece is really just t squared times 1, or t squared. So my radical here simplifies a lot. It's just the square root of 1 plus t squared. So I have integral 0 to 1, square root of 1 plus t squared dt. Not bad considering how horrific this thing looked at first. Does anybody remember how to do this integral? We've seen this integral several times in class.
This is an integration by parts, correct?
There will eventually be some IBP, I believe. But before we can go towards IBP, there's something else we need to do. Think about the section where you saw a lot of square roots of quadratics.
Do a trig sum, but I forget which one it is.
Yeah, Josh is correct. This is trig sum. This is like t squared plus a squared. This is a tangent substitution. To do this integral, we substitute t equals tan theta, which means dt is secant squared theta d theta. And we also change our bounds. When t is equal to 0, we have 0 equals the tangent of theta. So theta would be the inverse tangent of 0, which is 0. And when t is equal to 1, we have theta equals the inverse tangent of 1, which is pi over 4. So putting all of this together, our integral becomes integral 0 to pi over 4, square root of 1 plus tan squared theta times secant squared theta d theta. And this might be ringing some bells now. This is one of those challenging integrals. 1 plus tan squared, the thing underneath the square root is secant squared. So this is the square root. So integral 0 to pi over 4, square root of secant squared theta times secant squared theta d theta. The square root of secant squared is secant. So this is integral 0 to pi over 4 secant cubed of theta d theta. Now, I think it was Cody who said something about integration by parts, right? Does anybody remember exactly how we do the integral of secant cubed?
Secants, we convert one of the secants to tangents, correct?
Let's see. There's a few possible approaches here, but the normal one is to run IVP, which means we have to choose U and dV. I would choose U to be secant theta and dV to be secant squared theta d theta. So we kind of split it up like this. I'm not going to go through all of this. Du is secant theta, tangent theta, d theta, and V would be tangent theta. It's a looping IVP. It's not even a regular IVP. It loops. It's quite hard. And the result, oh, fuck it, we'll go through it. Oh, no, we got other stuff to do today. So the result after some looping IVP is that we get 1/2 times secant theta tangent theta plus the natural log of the absolute value of secant theta plus tangent theta. Oh, sorry, I'll use a bracket here because we're going to evaluate. This is a definite integral from 0 to pi over 4. So the secant cube integral, this is one that before the first test, a lot of people asked me, should I commit this to memory? Is this something I should try to memorize? Or is it something I should like go through the steps for on the test? Before the first test, I said, well, you can commit it to memory if you want, but if I ask it for you on a test, you'll need to show me the steps. At this stage in the course, I'll say, go ahead and commit this guy to memory. Right? The integral of secant cubed is 1/2 secant tangent plus the natural log of secant plus tangent. It's just gnarly, you know, it requires looping integration by parts. And it's really not worth your time to do it every time. It's worth your time to do it once. And then remember it. Just to be clear, in case you're panicking, this isn't a problem I would put on a test, right? We've had to do quite a lot to get here. And it wouldn't be fair for me to ask you to do all of this on a test. The purpose of this problem is just to show you kind of how gnarly these arc length integrals can get. Now, if we evaluate this at the lower bound, I would have secant of 0 times tangent of 0, which is 1 times 0, so that would be 0. And inside the natural log, I would have secant of 0 plus tangent of 0, which is 1 plus 0, and the natural log of 1 is 0. So no contribution from the lower bound, but at the upper bound, we get the secant of pi over 4, which is the square root of 2, times the tangent of pi over 4, which is 1, plus the natural log of the secant of pi over 4, which is again square root of 2, plus the tangent of pi over 4, which is 1. So this would be your arc length. It is, I'll distribute the 1/2. You have root 2 over 2 plus 1/2 natural log of root 2 plus 1. Root 2 plus 1 is positive, so I can ditch the absolute values. It's incredibly gnarly. Incredibly gnarly. And sort of the purpose of this problem is to demonstrate just how out of control these arc length integrals can get. In theory, one of the reasons we cover power series before talking about arc length is because just like some of those problems from your homework last week, many of these arc length integrals can only be solved using power series. And there are some excellent problems in the book that ask you to do that. I'm not going to ask you to do that, but it's worth at least acknowledging. So this is arc length. Some of the integrals are easy. Most of the integrals are hard, but setting them up is not terribly hard. Questions on either of these two examples here? that's really all I have to say about arc length. For you guys right now, it's really just about this formula and solving the integrals. There are some problems in your homework for you to practice. I don't think they will give you a terribly hard time, but if you get stuck on an integral, don't be ashamed to ask for help. Before we talk about polar curves, there's one other thing I want to share with you, and that's how to find surface areas. And you're going to learn a lot more about this in Calc 3, where you guys will do it not using parametric curves or any sort of rotation tricks, but you'll learn how to do surface integrals, which are quite cool and involve some work with differential forms. Here, because we don't have Stokes' theorem, we don't have Green's theorem, we don't have a mechanism for attacking those sort of integrals in higher dimensions directly, the only way we can find surface areas is like how we found volumes at the start of the class. Remember, in order to find a volume in this class, we had to have a solid with a lot of symmetry, usually rotational symmetry. So we're going to learn how to find surface areas for solids of rotation. The picture here, something like this. I have some curve, and I'm interested in working just between like A here and B here. I want to rotate that around the x-axis. We know that that'll produce a solid. I'll do my best to draw it here. Looking something like this, kind of like a flower vase on its side. And what I want to do is find not the volume of this, but I want to find its surface area. The trick to that is to look at a little piece of arc length, which I'll call ds. ds is a little differential piece of arc length. And recall, I want to call this curve, this is a parametric curve, right? So this is the y-axis, this is the x-axis, and the curve here is x equals x of t, y equals y of t. Recall that the arc length S is the integral. Actually, I shouldn't use A and B here. Let me just scratch these. I'm going to say this is the point associated with t equals A and the point associated with t equals B, the times, not the x values. Because that way we can use the same formula we did before. The arc length is the integral from A to B of dx dt squared plus dy dt squared, all under the square root, all times dt. Remember how we integrated dA to get A? We integrated the differential area to get area, or we integrated the differential volume dV to get V. Well, the thing that you integrate to get arc length S, we call ds. So the integrand here is ds, is this little length here. And in order to find the surface area associated with that tiny piece of arc length, you imagine rotating just that tiny piece of arc length. That would produce this little narrow band of surface area. So if I want to find the area of this little narrow band here, I treat it the same way we did back in the cylindrical shells method. I'm going to cut and unroll. So I'll call this little area, this little band of surface area, we'll call that dA, right? Differential area. And I'm going to give it to you in terms of ds. If you cut and unroll that band, you get a little strip whose lengths on the side here are ds. That's this little bit of length, that we rotated, and whose dimension in this direction is 2 pi times the radius. It's the circumference of the band. And that radius is the distance from my axis of rotation up to that band, up to that little piece of arc length. So this is the circumference, which is always 2 pi times the radius. And in this case, that would be 2 pi times the y value there. So your formula for surface area which I'll call A, is the integral from t equals A to t equals B of dA, which is the integral from A to B. There's a handful of ways to say this. My favorite way to say this is it's y times ds. This is rotated about the x-axis. But if you want to, you can plug in for ds. We know what ds is. So this is the integral from A to B of y times the square root of dx dt squared plus dy dt squared, all times dt. And if you wanted to rotate about the y-axis instead, you can draw the picture and think about it that way. Your ds would be the same, but instead of y, your radius would be x. So this is how I encourage you to remember it, is as y times ds or x times ds. I'll summarize these formulas on the next page. But first, I just want to check and see, are we comfortable with where this is coming from? Are there any questions about what piece is what or where the formula is coming from here? Okay, so let's summarize the results. Your formulas for surface area if you're rotating about the x-axis, then your surface area is going to be the integral from t equals a to t equals b of y times ds. And if you're rotating about the y-axis, the only thing in that derivation that would change is the radius. Oh, did I lose a 2 pi? I might have lost a 2 pi. Ooh, hang on, thank you. Let me check here. Yeah, sorry. So we've got 2 pi y, sorry. 2 pi y, 2 pi y. Thank you. Yeah, I'm so sorry. My circumference, this should be 2 pi r, 2 pi y times ds. My little dA. Yeah, thank you. So here we go. Two pi y times ds. Thank you. And if we're rotating about the y-axis, it would be the integral from t equals a to t equals b of 2 pi x times ds. And in both of these, ds is the little element of arc length. Dx dt squared plus dy dt squared, all under the square root times dt. There are some very fun examples here. You may remember the Gabriel's horn example that we played with back when we talked about volume. We said that the volume of this infinitely long horn was finite. I'd like to start with a slightly gentler example. Let's see what we've got. All right, so here we have a parametric curve, and they're asking us to find the surface area that we get by rotating that thing around the x-axis. Let's do it. X of t is t squared, t cubed, y of t is t squared, and t runs from 0 to 1. So example, I'll copy this down and we'll switch back over. Find the surface area of the solid generated by rotating x of t equals t cubed, y of t equals t squared, with 0 less than or equal to t less than or equal to 1, about the x-axis. Ideally, we would know what this thing looks like. And there's a bunch of ways to get a picture for that. We could eliminate the parameter. I can solve this y equation for t, or I could solve this x equation for t, and then plug the result into the other. So first, let me do that. First, to see the graph, eliminate the parameter t. This is what we were doing on Tuesday. Since I know x is equal to t cubed, that means that the cube root of x is equal to t. And then if I plug that into the y equation, I get y is equal to, well, it's t squared, but t is the cube root of x. So that's the cube root of x squared, which is x to the 2/3 power. So my curve here is a portion of the graph y equals x to the 2/3. This is a power function here. The power is strictly between 0 and 1. So we know it's going to have this concave down increasing shape in quadrant 1. we can also play some other games. As a function of x, this is symmetric about the y-axis. It's an even function. The graph y equals x to the 2/3, I'll just show you. It's this cool cusp form. I have my kids in Calc 1 play with this quite a lot because it's a good example of something with a vertical tangent. Looks like this. Now they've asked me to use just the t interval from 0 to 1. So that means my initial point